Hi all, today we get to take a little bit of a break from the number crunching on your calculators again. We are continuing on with thinking about three different types of solutions, but focusing this time on ionization, so specifically then on acids. Now, acids are one of those things that have come up in your past, but the ins and outs of properly naming them hasn't. And it's important that you know both ways of naming. So honestly, the way that we are, if you will, supposed to name them now is actually pretty easy. It involves the recognition that they're dissolved in water, which means they're aqueous, and the recognition that all acids contain hydrogen. That's a pretty big deal. So that easy method, that what we call a UPAC method, is great, but reality is the chemistry field is built on a foundation of an old way of naming acids, which is called the classical naming. Now, both of these recognize the ionization that happens when acids are placed in water, but the classical naming, I would say, is a little bit less intuitive. So we need to spend a little bit more time understanding how it works, learning how to name them properly, and then putting it into practice. And that's what you'll be doing today. So, couple things first. Do not lose sight, please, that acids form aqueous solutions. They are, in other words, in water. Do not lose sight that we have an H plus ion as a result, that hydrogen ion. And don't lose sight that there is an anion. Anion, by definition, is a negatively charged ion, and that anion is going to be super key to naming these properly. So again, let me emphasize, do not lose sight of the anion as we start to put this into practice. Okay, like I briefly mentioned already, the UPAC system is, in my opinion, the easier method. This stands for International Union of Pure and Applied Chemistry. And honestly, the beginning of this just involves literally writing down the word aqueous. Every single acid, when it is placed in water, no exception, is aqueous by nature. So that AQ is an integral part of the formula for an acid. Now, the rest then with UPAC naming, after you write down the word aqueous, is simply named as if it were an ionic compound. Now, not that they are, because they're undergoing ionization, but I'll show you what I mean. Every single one of these examples that is on here starts with the word aqueous, and that is par for the course for UPAC. The second part of this name is all based upon the hydrogen that has to be present in every single acid. So notice that consistency for all three of these examples: aqueous hydrogen, aqueous hydrogen, aqueous hydrogen. The last part is based upon that anion that we're talking about. And the anion, of course, is what changes. So if you look at this first one, this is a carbonate ion, right? Remember what I said to you? Memorize your polyatomic ion table. It really does come in handy. So that carbonate gets mentioned at the end of the name. Similar thing, this is Br negative, so it'd be the bromide ion, hence there it is. And this is a different one, guys. I want you to understand that when you look at your data table, we have a situation now when we're glancing at the table of polyatomic ions where this is just a snapshot of polyatomic ions. There's way more than what are written there. So each of these different ions, we can often get an idea of another one that would exist based upon the name. For example, check out phosphate. Phosphate is PO4 3 negative. Take note that there are 4 oxygens there. Okay, well, what if I have a different situation like this one where it's not PO4 3 negative, but PO2 3 negative. That's quite a change. So see what the differences are in this. This is phosphate, PO4 3 negative, and phosphate is on your table of polyatomic ions, but this one, as shown here, is phosphite. And it's not just phosphite, it's hypophosphite. The reasoning behind this is the phosphate has 4 oxygens, And the hypophosphite has 2 less. It doesn't even just have 3, it's got 2. So this is where the hypo comes from, saying, hey, it's way less. And this is where the ite comes from, saying it's less than it was. Okay? By comparison, guys, if this is hypophosphite, just so you can understand, phosphite by itself, without that hypo, would be equal to PO3, 3 negative. Compare these. Phosphate, phosphite, hypophosphite. And notice the oxygens. 3, 2, 4. Interesting. We'll come back to that afterwards, but just be aware that I'm introducing to you a new way that we can use the polyatomic ion table to figure out some more different polyatomic ions. Okay. Let's keep going. UPAC naming's pretty easy then, right? Aqueous, hydrogen, and the anion. Now we go into classical. This one has a little bit more of a trick to it, and you're going to have to spend a bit more time figuring out what's what. The key, though, is to focus on the anion, and that'll make a huge difference. If you have an anion that's an ide, then that's going to transform into, you have to put the word hydro first, and then that ide gets an ick. Now notice with these, we don't start with the word aqueous. Instead, for every single one of them, we acknowledge, hey, this is an acid, this is an acid, this is an acid. Okay? But take note again, ide, we put the hydro and the ick. Okay, go to another one. What if the anion ends in ate? Okay, that'll be like a sulfate, right? Then we don't put hydro anymore, and that ate gets replaced with ick. Another one. What if we have an ite? Like, for example, nitrite. This, when formed with hydrogen, is not going to be an ick, but an us. Otherwise, you pretty much keep the front part of the name of the anion. I'll show you what I mean in a moment. Do not lose sight, please, that every single acid, no exception, is an aqueous solution. It's dissolved in water. And don't forget that they all have hydrogen ions. So that classical naming acknowledges the aqueous with saying acid, and then the hydrogen, they're acknowledging it by being like, well, yeah, they just all have it in common. So we leave it off. Our focus is all about the negative ion, the anion. Let's put this into some practice. All right, check these out. These are all examples where we are dealing with ides. Now, by that I mean, and consider this, right? Bromide, chloride, nitride, and sulfide, right? All of these are ide endings, no exception. Now, we've got 2 different scenarios that are being listed here. The first one is the UPAC naming, that nice easy one, right? Aqueous hydrogen bromide, aqueous hydrogen chloride, etc., etc. You need to know how to do that, but it's much, much easier. Let's go into the classical naming. This is the one exception where you need to put that hydro in front when you are dealing with the ide on your anion. So all of those, hydro, but then notice what we do. We keep the brome, but instead of ide, that gets replaced with ick, an acid, hydrobromic acid. Chlorine follows the same thing. Chloride was there before. It's just HCl, hydrochloric acid. Nitrogen. We don't say nitrogic, right? We do similar to what we do with the nitride. So it would have been nitride. Instead, we take off the ide, we put ick, hydronitric acid. Perfect. Couple of exceptions. Sulfur and phosphorus are just kind of weird in terms of how we name them and how they transfer over. So if we had sulfide before, we don't put hydrosulfic acid. Instead, just please be careful and take note. We add that little UR, hydrosulfuric acid. Similar type thing if we had phosphorus. So if we were dealing with, for example, our H3P, right, phosphoric, then we don't say hydrophosphoric acid. We say hydrophosphoric acid. just to take note that this little or is hanging out there. Okay, that's with your ides. Ide turns into hydro blank ic acid. Let's move on. What if you have an anion with an ate ending, like nitrate, for example? Again, that lovely U-Pack naming is really, really simplistic. Aqueous hydrogen nitrate. Aqueous hydrogen carbonate. Keep going down. Aqueous hydrogen sulfate. Aqueous hydrogen, ooh, here's a fancy one. Remember what we were talking about on the previous page where I was saying, hey, phosphate, PO4 3 negative. Hey, phosphite, PO3 3 negative. Oh, look, hypophosphite, PO2 3 negative. Now I'm introducing another one to you. This is the wonderful world of perphosphate. Again, this is not actually on your polyatomic ion chart, but it has 5 hydrogens instead of phosphates, PO4 3 negative. How do we show it has 5? We add this word in the front, per. Okay, I'll give you a little cheat for that in a while here. But regardless, here's your anion, perphosphate. Look at how these goes, guys. If we have an 8 as the ending on the anion, you no longer write the hydro when you do the classical naming. It's gone. Instead, we leave it off, and it's nice and simple. That 8 ending gets replaced with ic acid. So it is not aqueous hydrogen nitrate, it is simply nitric acid. Look at the carbonate. We take off the 8, put on ic acid, carbonic acid. Similar to what happened with sulfur and phosphorus before, they're kind of weird. You have to add the UR. It's not just sulfic acid, it is sulfuric acid. Okay. Similar thing here too. And this one, we end up with not just perphosphoric acid, it is perphosphoric acid. Sulfur and phosphorus are weird. They make you have to name them slightly differently. Let's check out our last scenario. Not an ide ending, not an ate ending, but an ite ending. With ites, it gets changed into an us, O-U-S. Go back again to that U-Pack naming. U-Pack, that aqueous hydrogen is always going to be there. And then we name the anion, which in this case is nitrite. Remember what I was saying, ite ending. Instead of this becoming nitric acid, it is nitrous acid. So us goes with the ite. Aqueous hydrogen chlorite becomes chlorous acid. Again, look at this one. Aqueous hydrogen hyposulfite, ITE, becomes us acid. And once again, sulfur's weird, so we got to add on that UR. Okay, hopefully this is feeling okay. Let's put it into a little bit of practice with a cheat that is actually built into your periodic table. So go over to your data booklet, and I want you to look at that polyatomic ion chart, and let's focus right here. Now, I know those funny little prefixes were kind of difficult, but I want you to see something here. When I have 8 with nothing in the front of that chlor, that's when I have what I would call the normal number of oxygens for this scenario. In this case, it's 3. So what if then we go to a situation where you add one extra one? So we're not at the normal, we'll say, we're at one more, 4. This is where the per gets added in. The 8 is still there, but per is put add as an additional one. Okay, go to one less. One less, we're down to 2. This means that we change it to an ite ending. And what if vice versa then? We go a little bit further and we're down to a single oxygen. You can write these lists in 2 different ways. We keep the ite, but then we add a hypo. So take note, per is when there's an extra oxygen from what would have been. Hypo is when there's 2 less oxygens from what there would have been. This here, the chlorate is my normal, and chlorite is 1 less. Okay, keep that in the back of your head. It's a built-in cheat sheet that's right in the middle of your polyatomic ion chart. All right, let's try this. You have this empty table in your notes as well, and I want to make sure that you can name them, and we're going to base this on all of those ones with chlorine in order to make sure that you've got it understood with the cheat that's on there. Classical name is the one that's harder, right? The UPAC name, for every single one of these guys, you can right away take it as, yeah, it's going to be aqueous, hydrogen, something, right? Aqueous, hydrogen. You should write these down in full on yours, but I'm just for the sake of time doing it this way in here. Aqueous, hydrogen, something, aqueous, hydrogen, something. The something is always going to be the anion, right? And I pulled out the accompanying anion for each of these. You can see how it combines with hydrogen to make the actual acid. So aqueous, hydrogen, and that's an anion by itself, a singular one, aqueous hydrogen chloride. Look at the next one. Aqueous hydrogen. This polyatomic ion is on your table. It is perchlorate. So we write it down exactly as it is. This is also on your table. Hence, it's a nice cheat. Aqueous hydrogen chlorate without the per. The next one, aqueous hydrogen chlor. Notice how this has changed now. No longer ite, but ate. And now we're down to a single oxygen, aqueous hydrogen hypo, saying, hey, there's way less here. Hypo, oh, come on, pen. Chlorite. I-T-E. All right, classical name then. This one has the "ide" ending. If it has the "ide" ending, we need to include the hydro. Oops, that's not going to work. Hydro. Then we put the chlor that would have been in chloride, except instead of "ide," we put the "ic" acid. There it is, hydrochloric acid. This one was the perchlorate ion. Hydro is gone because it's not an ide. It becomes perchlor, and no longer ate, but ic acid. Notice what's been added on here. Hydro for the first one, ic acid. For the second one, we still keep perchlor, but then we add ic acid. Okay, look at the next one. This is chlorate. So I keep the chlor, and instead of ate, I replace it with ic acid. Ic and acid. Go to the next one. This is chlorite. So again, I keep the chlor, but instead of ite, it's replaced with us. Chlorus acid. There we go. And our very last one as we go is HClO, which is hypochlorite. So we have to include the beginning of the anion, hypochlor. And then instead of it being ite, it becomes us acid. Us and acid. And that's all there is to it. That classical naming, without a doubt, is a little bit more of a challenge. So spend some time. There's a bit of memory work put into this, and there's quite a sheet that accompanies this in order for you to do your homework. Guys, this is number 2, and I'm going to caution you that there are definitely some polyatomic ions on there that are not on your polyatomic table. But you can do this. For example, if this is carbonate, well then what's this? Oh, this is carbon. There's one less. Ite. Or vice versa, whatever I put an extra one. CO4, 2 negative. This is not carbonate. This is because there's an extra. Carbonate. Okay? Look to help yourself by looking at what that chlorine one does, where you have perchlorate, chlorate, chlorite, and hypochlorite. There's the pattern that's right on your data sheet right here that can help you to interpret the other ones. All right, guys, good luck with this. As always, let me know if you have any questions.